Okay, Assalamualaikum warahmatullahi wabarakatuh. Okay, this is our next topic, which is the topic of chapter 9, flow over bodies, which is drag and lift. So this is our second last chapter. So in these topics, we will learn about the drag and lift, friction and pressure drag, drag coefficient of common geometries, parallel flow over flat plates, flow over cylinders and spheres, and also lift. Okay, what is lift and drag? Okay, drag force acting on automobile, power line, trees and underwater pipelines, and lift mostly developed by airlines wings. So the transportation of red blood cell also related with a drag of blood flow. Okay, then the entrainment and disbursement of the liquid droplet by spray. So the vibration of noise generated by bodies in a fluid and power generated by wind turbine. So these all some of example related with drag and lift. Okay, in fact, drag and lift also related with bodies subjected to fluid flow are classified as being streamlined or blunt depending on the overall shape. Okay, for example, we can see here. Okay, you can see there is a few example of a long cylinder 2D, a blunt asymmetry of bullets, and also car 3D. So the streamlined body such as a race cars and airplane appears to be contour and slicks, and otherwise such as building tend to block the flow and it's said to be bluff or blunt. So the drag and lift happen especially the moment the flow being obstructed by a blunt body. Okay, so from there we can see the streamline of the flow start to be diverge. For example here, so the flow start to be diverge due to the effects of the obstruction. Okay, usually it is much easier to force a streamlined body through a fluid, and thus streamlines lining has been great importance in design of vehicle. Means that in order for us to study the streamline, it's easier for us to have a blockage of that model, and by implementing the flow we can study how the flow behavior towards the blunt body. Okay, so body meets some resistance when it forced to move through fluids. So you can see here in this picture we have two type of cars, which is the old design of cars and the new design of cars. If you can see here, when we fix it, the speed is constant for both of it, which is 60 miles per hour. With difference design of car, we notice that for the first picture we need 70 horsepower in order for us to move the car. Meanwhile, with the new car with more aerodynamic shape, we can reduce it, only use 50 horsepower due to the effects of aerodynamics. So this is the importance of the understanding the drag effects or resistance effects. So the more aerodynamic of the body will produce lesser resistance. So this is high-speed bike from Delft, Netherlands. So you can see there is a lot of aerodynamics effects shape in order to reduce the drag effect. Okay, a fluid may exert force and moment on a body in and about various direction. Okay, the force flowing the fluid exert on the body of flow direction is called drag. So if you can see on the right side, this is one of the equipment to detect lift and drag. Okay, so the force measurement system for the aero rocket wind tunnel. So if you can see here, based on here you can detect the drag using the spring effects and also the lift. Okay, the drag force can be measured directly by simply attaching the body subjected to the fluid to a calibrate spring and measure the displacement in the flow direction, just like measuring a weight of spring. So when we put the rocket here with this equipment, for example, we run a flow here, blow a flow here, so the rocket will be moved. So the movement happen here will give some force due to the spring effects of the distance. Okay, more sophisticated drag measurement device called drag balance use flexible beam fitted with strain gauge to measure the drag electronical. So we have this equipment in our aerodynamic lab. So maybe one point of time you will have experience to use this equipment. Okay, this is the image of how it works. We put it in, for example, in the wind tunnel. So the flow will be flow from the inlet, and we put the model here. So the moment there is any movements of the model, so it will give us the result based on the strain gauge. So the distance of the strain gauge, so we can calculate the drag and also the lift. Okay, so in this slide we can see there is the effect of lift and drag. Okay, if you can see the first example, in this example shows that the flow passing through a block. Okay, so what will happen is, due to this blockage, the streamline start to be happen, low recirculation happen at the back of this plate. Okay, so what happened here at the front area, it will produce a wall shear and also high pressure. Meanwhile, at the back will produce a low pressure. So confluence of high pressure and low pressure will produce recirculation flow. Okay, the bigger the blockage, the more recirculation happen and the higher drag will be produced. So from these effects, we can relate with, for example, aerofoil wing. If you can see here, based on this streamline of the aerofoil, we can see there is a positive and negative pressure effects. Okay, based on Bernoulli concept, the low velocity produce high pressure and high velocity produce low pressure. Based on here, the below part of the airfoil produce positive pressure, which help, and in fact the upper part of the airfoil surface produce the negative pressure. Okay, negative pressure. So here produce a positive pressure. What happen is lift happen. Lift, the high pressure will help the airfoil to produce a lift for the wing. Okay, so lift is normally in the x direction going up, and also drag is in the lift in the y direction, and x is in the for drag direction. Okay, so this is the reality of wing. So when the flow flowing from the front, it will produce a lift and also drag. Okay, this is how the theoretical of the wing. So this is a chord line. So this is angle of attack. So angle of attack is the movement of the airfoil will produce lift and also drag. Okay, we go for example. Example 1 shows that a car with design condition of 1 atm, 70 Fahrenheit with 60 miles per hour is to be determined experimentally in large wind tunnel in full scale test. the front area of the car is 22.26. So we know that the front area A is 22.26 feet square. If the force acting on the car in the flow direction is measured 68 lbf, means that the F force D, okay, of the drag, the force acting on the flow direction, so means is a force drag is 68 lbf. Determine the drag coefficient. So the question asks us to find drag coefficient, so means CD. Okay, so we know we have previously, okay, we have two type of formula, which is drag coefficient. CD is equal to FD. FD is drag force divided by 1 over 2 rho V squared A. So meanwhile for least coefficient is CL is FL divided by 1 over 2 rho V squared over A. So based on these two formula, we can calculate the answer. So in these questions, this question asks us to find CD. So based, we know CD formula is CD is equal to 2FD divided rho V square A. So in this case, we know that the FD is 68 lbf. So divided by rho, in this case our rho is 0.07489. Okay, so our area is A is 22.26 and our velocity is 60 miles per hour. We change it to be feet per second. We should time is 1.467. So 60 times 1.467. So at the end we will get our CD is 0.34. Okay. Okay, next we will learn about the friction and pressure drag. Okay, the part of drag that is due directly to wall shear stress is called skin friction drag, or we can just call it friction drag or FD. Okay, since it is caused by frictional effects, and the part that is due to directly to measure P is called pressure drag. Okay, it's also form of drag because of strong dependent on form of shape of the body. The friction pressure drag coefficient is based on this formula. Okay, in order to calculate the drag coefficient, okay, the friction, so friction, FD friction is force friction divided by 1 over 2 rho V squared A. If for pressure drag, just now is friction drag, pressure drag is pressure coefficient drag is equal to pressure drag divided by 1 over 2 rho V squared A. So when friction and pressure drag coefficient or force is available, so the formula should be add up. So in order to calculate the coefficient of drag, so is equal to coefficient of friction plus coefficient of pressure drag, or same as drag force is equal to coefficient drag friction drag plus pressure drag. So this is for total drag force or for total coefficient of drag. Okay, this is in terms of image, the difference between friction drag and pressure drag. Okay, this is, for example, we have a plate which is parallel with the flow. So in this case, the pressure drag can be assumed to be 0 because of less pressure happen, but the friction drag at the surface is higher, so we call it as, in this condition, we call it as friction drag. If we change this plate in tangent position with the flow, so what happen is the obstruction will be higher. So what happen, the pressure drag will be reduced or higher. So this is, for example, a flat plate. But if we have an circular or aerodynamic force, so we will add up between the friction at this surface at the circle and also the pressure at the shape of this circle. So in order for this type of shape, you need to add friction and also pressure drag. Okay, at low Reynolds number, most drag is due to friction drag, but high Reynolds number, most drag is due to pressure drag. So means low Reynolds number, mostly friction drag happen, and high Reynolds number, mostly a pressure drag happen. Okay, so Reynolds number basically is inversely proportional with viscosity of fluid. So we know that the formula of Reynolds number is rho VL over mu. So means Reynolds number is proportional with the density of the fluid. Means if we have higher density, we will produce higher Reynolds number. Lower density, so if density is high, we will produce, so this is, for example, this one is constant, density high will produce low Reynolds number. But if your density is low, we will produce high Reynolds number. Okay, so this is the friction and pressure drag. Okay, what is pressure drag coefficient? Pressure drag coefficient most significant when velocity too high. Okay, so when you have high velocity, pressure drag coefficient happen. So means the fluid separate from the body at some point and create very low pressure region in the back. The pressure drag in this case is due to the large pressure difference between the front and the back of the body. So means when you have a high velocity, the pressure difference is higher. So due to that issue, there is a low pressure and high pressure at the front and also the back of the body, which produce the pressure drag. Okay, proportional to the frontal area and the difference between the pressure acting on the front and back of the limos body, the pressure drag is usually dominant to blunt body, small for streamlined body such as airfoil, 0 for thin body which is parallel to the flow. Like we mentioned previously, the blunt, the higher or the dominant will dominate in terms of the blunt body. For example, there is a bullet, so this one have higher pressure drag. Okay, compared to airfoil, which is have a lower, and if you have a flat plate, so the drag can be assumed as 0. Okay, for example, large commercial airplane increase their wing surface area and thus the drag by retracting the wing when they reach cruising altitude. So this is based on the pressure drag coefficient. So we use this concept to reduce the speed of the aircraft, especially when reaching cruising altitude. So if you can see, there is a flap or aileron here. So before landing, normally we can see that the aileron or the flap will be open in order to increase the drag pressure. So when we increase the drag pressure, automatically what happen is we reduce the speed of the aircraft. Then we can easily landing due to this pressure drag effects. So not only we cannot say that pressure drag is for example, in terms of aerodynamics fall, pressure drag should be less, but in terms of to reduce the speed, we should have higher pressure drag. Okay, this is more details. Okay, if you can see here, there is a flap mechanism. In order to reduce the increase the pressure drag and to reduce the speed, so what happen is this flap will be moving down. So means you will have a higher friction and pressure coefficient. Okay, just now we learned about pressure drag coefficient. Now friction drag coefficient. Friction drag coefficient normally is happen at laminar flow, independent on the surface roughness, and turbulent flow depend on the surface roughness due to the surface roughness element protruding further into the boundary layer. Okay, and it's proportional to the surface area. Body with large surface area experience a larger drag. For example, large commercial aircraft reduce their total surface area and thus their drag by extending their wing extension when they want to reduce the speed during the landing, as I mentioned previously. So the bigger of the shape of airplane or car will have a higher friction drag compared to the smaller design. Okay, this is the picture of an airfoil. So the variation friction pressure and total drag coefficient of the streamlines strut with thickness to chord length ratio for the number of 4 times 10 power of 4. So we note that CD for airfoil and other thin body is based on planeform area rather than the frontal area. So if you can see here, there is a two type of friction, which is friction, so two type of drag, which is friction drag. Okay, another one is pressure drag. Okay, for pressure drag, instead it will increase little bit based on D over L. So means the ratio, the higher ratio produce higher pressure. Meanwhile, for the friction, the higher ratio of D over L will reduce the lower friction drag, and the total drag based on assumption of both of it produce a total drags. That's why we cannot only see the effort of drag only, but we also need to check the D over L in order to produce which one is the best friction drag and pressure drag. Okay, this is an example of a wing with angle of attack. If you can see here, the first is 5 degree angle of attack, second is 15 degree angle of attack, and the third is 30 angle of attack. So at large angle attack, usually 15, flow will be separate completely from top surface of airfoil. So it reduced drastically, causing of stall. So we call it stall. So means the higher angle of attacks will produce recirculation of separation point at this area. Okay, so this is the example. If we go detail for the flow, there is happen separation point. So the flow will be have separation in this starting of separation point, produce a separated flow region. Okay, Okay, so the drag coefficient is in general depend on Reynolds number, especially Reynolds number below 10 to the power of 4. At high Reynolds number, the drag coefficient, most geometries remain essentially constant. So this one is the graph of drag versus Reynolds number. So we can see that when the Reynolds number increase, the drag start to be decrease. Means that then at one point when the higher Reynolds number happen, the drag start to be constant. Okay. Okay, this is the geometry coefficient, drag coefficient of common geometry. Okay, if we have, for example, 4 type of shape here. For sphere, the CD is normally 24 divided by Reynolds number. When we cut it to half of hemisphere, so the coefficient of drag will be 22.2 divided by Reynolds number. If circular plate, the CD is 20.4 Reynolds number. If it's a circular plate at a parallel position, so the drag will be reduced with 13.6 divided by Reynolds number. So this is drag coefficient at low velocity. So with this concept, for example, is important in designing a parachute. This is example of using this concept to design to reduce the speed of the parachute because of the shape. Okay, if you can see here, the first shape have a CD of 0.4. Meanwhile, the second shape has higher CD 1.2. So in order to have a high drag coefficient of body, can drastically change the body orientation and produce higher drag and reduce the speed of the box, for example. Okay, this is the example of feet folded back and brick extended of a bird. The bird teach us lesson on drag reduction by extending their brick forward and folding their feet backward during the flight. So this one is one of phenomenal that teach us how to reduce drag. So for airplane which looks something like bird, so they retract their wheel after takeoff in order to reduce drag and to reduce the fuel consumption. Okay, in this picture it shows the streamline of 4 different picture with 2 different design of car. At the same real number, we can see that there is streamline around the design. Modern car closely resemble the streamline around the car in the ideal potential. Assume neglect friction except near the rear and resulting the drag. If you can see, the first design produce higher drag because of higher obstruction compared to the second design, more aerodynamics, the flow move smoothly compared to the first one. So this one will produce higher drag compared to this one will produce lower drag. So that's why aerodynamic important to reduce the drag effect. Okay, this is another example of 2-person cycling. So what we can notice that the first person will have higher pressure and higher drag because of he facing the flow, the air, and it produce higher pressure. Meanwhile, the second one take the advantage to have a low pressure because of due to the effects of the flow, the less pressure, low pressure in the middle. So the second person have a lesser drag coefficient. friction, okay, drag coefficient of body. Okay, this is the shape of drag coefficient. If you have a square drag coefficient, most probably this is in 2 dimension at the real number is higher 10 power of 4. So if you can see here, for rectangles the CD is 2.2, but if you have a round shape, the CD reduced to 1.2. Okay, for rectangle sharp corner we use this table. Meanwhile for rounded edge we use second table. Same as circular, for lamina is 1.2, turbulent is 0.3. For elliptical we use this table. There is difference between lamina and turbulent due to L over D. Okay, so the third one is the triangle. So if the flow facing this angle, okay, so the drag is 1.5. If facing the larger surface, the drag will be increased. Same like semicircular shape for the U shape will produce higher CD compared to the another shape. Okay. Okay, this is the development of boundary layer, flow over a flat plate with different flow regime. So the first is, for example, lamina. So in this lamina, so the boundary layer is smaller, and towards the turbulent, the boundary layer will be increased due to the turbulent layer overlap of buffer. Okay, the development of boundary layer on surface is due to no slip condition of the friction. Okay, so for CD, for flow over a flat plate, CD we can assume as 0. For CD friction equal, or sorry, for CD pressure is 0. For CD friction is CF or FD, force drag pressure is 0, and force drag friction is CFF or CF times A rho V square over. Okay, this is the variation of local friction coefficient for flow over a flat plate. Note that the vertical scale of the boundary layer is greatly exaggerated in the sketch. Okay, now this is the formula for CF, coefficient of friction. Okay, coefficient of friction for lamina in the range of real number 5 below 5 to the power of 10 power of 5. So we use 1.33 divided by square root of real number. But in turbulent, in between 5 power of 10 power of 5 or 10 power of 7, so the formula is 0.074 divided by real number power square root of 5. So this is turbulent real number, this is laminar. Okay, so this is example number 2 is there is an engine oil at 40-degree flow at 5 meter long flat plate with free stream velocity of 2 meter per second. Determine the drag acting on the flat plate. So we know this is the flat plate, the length is 5 meter and the velocity is 2 meter per second. So the question is asks us to find the drag force. So based on previous, we need to calculate. First question is calculate laminar or turbulent. So first is calculate real number to get laminar or turbulent. So from here you can decide. So the second step, okay, we know, okay, we go for one by one. Real number is VL over nu, okay, which is our V is 2 meter per second, our length is 5 meter, and our nu is 2.485 to the power of negative 4. So here we'll get the Reynolds number of 4 to the power of 10 to the power of 4. So we know here this is below than 10 power of 5. So automatically, okay, this is below than 5 to the power of 10 power of 5. So automatically we know this is a laminar. So based on the laminar flow, we can decide from here. So we need to use the second one is formula of CF for, in this case, laminar. That's why Reynolds number is very important. If you calculate differently, you will find different solutions. Okay, for the laminar, the formula of CF, okay, CF, which is coefficient of friction, is 1.33 divided by the square root of Reynolds number. So here is 1.328 divided by square root of Reynolds number. So our number is 4.2024 times power of 5. So at the end we will get CF is 0.00662. So we know that the pressure drag is 0 because of it's a flat plate, because of the velocity, the inlet velocity is parallel with this plate. So we know that for CD pressure will be equal to 0. So we only have CD is equal to CF. So in order to calculate the drag force, the third is calculate the drag force. So drag force is equal to CF A rho V squared over 2. So CF we already get, just put it here. Then our area is 5 times, we assume here to be 1 meter per second. Okay, then the rho is 1876, the velocity is 2 meter per second divided by 2. At the end we'll get the force of drag is 58 Newton. Okay, this is the graph of average drag coefficient for cross flow over a smooth circular cylinder and smooth sphere. Okay, so how the smooth sphere and also the sphere graph. Okay, this picture shows the flow visualization of flow over as A is a smooth sphere at the number of 15,000, B is a sphere at the number of 30,000 with a striped wire. So the delay boundary layer separation is clearly seen comparison of two. So if you can see here, there is a separation flow happen here. So for lower Reynolds number is much clearer compared to the high Reynolds number. Okay, this is the wing. There is a lift and drag same as previously. So this is a chord, this is a span, we call it chord, this is span, then angle of attack based on here. Okay, so here is the airfoil contribution of viscous effect of lift is usually negligible since wall shear is parallel to the surface and thus nearly normal to the direction. So this is the direction of lift, this is the direction of drag. So this is angle of attack. When we change the angle of attack, the lift will be different and the drag also will be changed. Okay. Okay, this is the figure shows the three concept of wing. Okay, here we can see there is three types of wing. The first is a rotational flow past a symmetry airfoil. So zero lift. because of this airfoil is symmetry, we notice that there is a two stagnation point happen at the beginning and also at the end. So it produce of zero lift. Okay, the second one, there is a non-symmetry airfoil. So this also produces zero drift because of the stagnation happen at the beginning and also happen at the surface of the trailing edge. Meanwhile, the actual flow past a non-symmetrical positive list when the stagnation at the beginning and also the stagnation happen at the end after the wing. So there is a rotational actual flow past and non-symmetrical to airfoil. If you can see here for the second picture, there is a, due to this shape, what happen is there is a the flow are not smooth, but the actual flow past the flow will be smooth. Okay, so this figure shows the wing shortly after a sudden increase of angle of attack. A counterclockwise starting vortex is shed from the airfoil. Okay, while clockwise circulation appears around the airfoil, causing lift to be generated. So when the wing is moved clockwise, okay, what happen is we will produce a vortex, the flow at the tail. After the tail, there is a vortex happen. The vortex will happen after the tail. So the vortex is produced of anti-counterclockwise. Okay. Okay, this is the graph of CL over CD towards angle of attack. If you can see here, the CL over CD will be increased when we increase the angle of attack, but until there is one point, for example here is 4 degree angle of attack, there is the CL over TD, means the drag, the lift over drag start to be reduced. So we call this as a stall condition. So this one we call it as a stall angle. So we need to understand the wing are not, when you increase the angle of attack, keep on increasing, there is one angle of attack which is we call stall angle. After the stall angle, no more producing a good lift and also less drag. So you need to know each of the wing have a different angle of attack, stall angle of attack. So the higher stall angle of attack better than the lower stall angle of attack. That's why research is keep on improving the airfoil shape. For example, NACA, we have a lot of series NACA. We have NACA 4415, NACA 0012. Okay, so we also have a for example S foil. If you have silic foil, so a lot of pattern of airfoil. So keep on producing the performance of the wing. Okay, so this figure shows a non-lifting body and lifting bodies. In non-lifting bodies, the total profile drag is happen due to the screen friction drag and pressure drag. Meanwhile, for lifting body, there is a effect of profile form, which is screen friction, pressure friction. We also add up a induced drag. So total drag for lifting body, there is a induced drag, but total drag for non-lifting body, there is no induced drag. Okay, thank you.